What we are discussing are gases recently. And there are two descriptions of gases. One of them is called, that's maybe the most difficult word I know, phenomenological. Another one is called statistical. Okay. So we'll be using both of the description of gases. First, we start with the phenomenological one, and later statistical one, and later we connect them together. So now first, let's make the origin of the name. Origin of this one comes from the word phenomenon. Anybody knows this word? Yeah, what is in Chinese? Oh. You know phenomenon? Yes, that's the same in Russian. Which means something you can observe, some event, some happening that you can measure, observe, see, touch, whatever. And the name phenomenological means that this is everything about gases that you can measure in experiment. So the description of the phenomenological gases will include such parameters as pressure, volume, mass, temperature, density. What else? Well, as you will see that later when we go to the thermodynamics, there are many other parameters, U, H, S, and such like pressure, volume, mass, temperature, density, heat at constant pressure, heat at constant temperature, internal energy, enthalpy, entropy. There are other parameters that you can measure. Good. Well, the other description is the statistical description coming from the word statistics. Okay. And the idea here is, in the phenomenological description, you completely don't care what is inside. How many atoms, how they look, if they are green or red, whatever. It's not important. You just have big box of something. You don't know what is something. In the statistical approach, it's opposite. You care for every single one. But the statistics means that you have very large group of objects that behave similarly, but not the same, just similarly. But each of them is different. So for example, for this class, the statistics, I can make the statistic of height. There would be some number as an average. And then we can describe, if I do the height of this class, I would have a curve, and the average would come somewhere here, then would be the dispersion of this curve, and so on and so on. So in the statistical thermodynamics, you are just accounting for the properties of single molecules inside, but there are so many of them that you are only interested in the averaged values. So the things that you are interested really is the average kinetic energy, the average potential energy, the average speed. Now with this one is a big problem. Speed is a vector, a particle can go here and here with the same probability. So on average, this one is 0. It's not interesting. So what we really are interested is this, v square. This square is not a vector anymore. What else? You can think about the momentum, again, square of every particle, and many other things. This notation means average. Since somehow conceptually it's easier to operate with pressure, volume and mass and temperature, however, maybe it would be very difficult to explain what temperature is. What is temperature? What about mass? What is mass? You see, when I ask a question, it's difficult to explain. But when you ask a question, what is entropy? Everybody says, no, entropy we don't know. We never studied. This is difficult. What I mean is mass is equally difficult as entropy. Just mass, you know from a child. But entropy, you don't know from a child. You don't have intuition. Similar thing is with pressure, volume, and mass, and temperature. Yes, Nina? Can I say what is entropy?
No, I can say.
You can say what is entropy. So but you cannot say what is mass. Interesting. Good. Good. We'll ask you for the definition of the entropy when we come to it, probably in 1 month. Good. What I wanted to say that most of the things here you know, but you cannot explain. If you really come to the question what it means, you become quiet and you start thinking, I don't know myself, to be honest. Somehow I know how to use them, and that's the important thing. But what they really are. But the statistics, it's easier, because really velocity and kinetic energy, they are kind of well defined. They are easier to understand. And what is the good point is this line. We'll be studying the connection between these two things. So we will explain what the temperature really is, or the pressure really is, in terms of the velocities of every particle inside. But that will come later. Just what we need to do today. Today we start with pressure. What are the units of pressure that you know? Units of pressure. ATM. Good. What is the name of ATM? That would be the atmosphere. And what is the meaning of atmosphere? That's a term from geography. How do you say in Chinese? Okay, so 1 atmosphere. If you have our Earth here, the Earth has some mass, and this mass is causing gravitation. And this gravitation is keeping all the gases around, and these gases are called atmosphere. Okay, so this is atmosphere. So now what is the pressure of 1 atmosphere? It's the pressure of 1 atmosphere. If the Earth has 2 atmospheres, that will be the pressure of 2 atmospheres, but the Earth has only 1 atmosphere. So the pressure outside today is around 1 atmosphere. It's changing every day because it depends on temperature. But generally the idea comes from this, that this is the pressure from 1 atmosphere of Earth. Okay, what are other units? Pascal, good. And Pascal is defined as one Newton over 1 square meter. Okay, so this looks like scientific definition. Because atmosphere, as you see, it's not very scientific. It's just atmosphere. It's changing all the time. Some gases are going away, some other are coming from cosmos. What is the connection between atmosphere and Pascal? I don't know. But it is 1013.2.5 Pascal. Other units? Torr. Good. And this one we defined, it's coming from the name of Torricelli, right? The guy who first time made a following instrument. He took a glass tube, no, how it looks like, I don't know, it's in the book. Let's say it's like that. It's open on one side and closed on the other side. Then he put inside mercury. And probably at the end there is some air. So the level is here. So now when the pressure here is large, then it's pushing this line up. But when the pressure is low, it goes the opposite direction. So he put a scale here, starting from 0 and finishing at, good question, I don't know where it finishes. But if you open your book on chapter 4, I guess there is a photo of this thing. This is the apparatus used for this. The figure 4.5 on page 129. Well, and usually, on the usual day, the scale is showing 760 millimeters. If it would have different length, it would be different number, but it's showing 760 millimeters. And this 760 millimeters is called 1 torr. Yeah, I'm saying something. This is 760 torr. I mean, to be honest, nobody is using this anymore, so, but you should learn. Right, this is 760 torr. So 1 millimeter of mercury is called torr. So you have again 1 atmosphere equals 760 torr. As you see, Pascal is not very good unit to use in everyday life. What is the unit to be used instead of Pascal when they are giving in the TV the pressure for every day? By the way, coming to pressure, I don't understand why, but in my country, in Poland, every day thousands of people put on TV to listen what is the pressure the next day, because they believe that high pressure they will be smiling, and low pressure they will be crying and tired all the day. I heard that in Bulgaria is the same, but I didn't meet any other country that believes the same. What about Taiwan? No connection, right? Ukraine? No connection either. But if you ask somebody in Poland, is it scientific? Yes, it's extremely scientific. And people believe it. So sometimes wives said to husbands, don't get close to me, today is low pressure. Strange. Okay. So we discussed pressures. Yes. Now let's go further. I've forgotten to say what is the unit. Yes. Because in TV they must use the good units. So they're using pascals, which is the SI unit. But saying the pressure today is 10,132 doesn't sound very good because nobody can remember so many digits. That's why usually they use the unit which is called 1 hectopascal. I think it's spelled as hecto. Okay, we can continue. I'm lying to you now. It would be different. 100 Pascal is 1 hectopascal. Yes, that's good. And now they're usually saying that the pressure is around 1000 hectopascal. Okay, yes, that's correct. 100? 100. Good, yes.
1,000.
You mean 10 to the 6th? Oh. Should be 5 zeros, right? Okay. Just to avoid all the problems, table 4.1 in your book is giving all the units and all the changes between them. Just to avoid any problems, I just copy this table. Thank you, Nina. So we have 1 Pascal equal 1 Newton over 1 meter square. Then we have 1 atmosphere equal, you're right, yeah. 3 to 5 pascals. Then they use something like 1 bar. And 1 bar is 10 to the 5th of Pascal. And this one is usually used for techniques. If you have a car and the car has a tire, usually the pressure for the car is given in bars. And then they have the 1 atmosphere is also equal to 760 torr or to 760 millimeters of mercury. So there are many different ways of saying the same. And your book is also giving the American one, pounds per inch square, but we are going to skip this one. Good. By the way, what does it mean high pressure, atmospheric pressure? What is low pressure? What is the highest possible? I said on a usual day, it's around 1000 hectopascal. So usual atmospheric pressure. When you have the lowest possible pressure on the surface of Earth. Okay, on the top of very high mountains. This is true. Good explanation. And in Taiwan, during typhoon times. If you have a typhoon, the typhoon usually looks like something like, my drawing is never good, but, and the lowest pressure is in the middle. How low? If this is 1000, what is the pressure inside? 950. 950 hectopascal. And the last typhoon, that was the strong one, it has 925. So it's very, very low. So usually they measure what is the pressure inside to tell how strong is the typhoon. Good, that's everything what you have to know about pressure. And now let's go to the fundamental laws of phenomenological gas theory. And there are three basic laws. One of them is called Boyle's law. Saying that the pressure of any gas and volume of any gas is a constant at T equal constant. It means if you have a box with gas inside, and now you are going to change the volume twice, then the pressure will go down twice. So at the beginning, the pressure and the volume was PV, but at the end, when you remove the border between them, the pressure nu is going to be half of the pressure, and the volume 2 is going to be double of the pressure 1. It means if you multiply them together, nothing changes. You know it from the high school. Next one is called Charles' law. Saying that V if you give higher temperature, the volume will get larger too. And it's a linear scaling. But here you should be careful, because the temperature is the temperature in Kelvin. Okay? So when you change the temperature from 10 degrees Celsius to 20 degrees Celsius, the volume will not get twice larger. Okay, you have to be careful with this one. But what does it mean? If you go with temperature to 0, does the volume go to 0? Again, not, because the temperature is Kelvin temperature. Kelvin temperature doesn't go to 0. It goes to 0 in the Kelvin scale. But the point is that before it happens, before it goes to the 0, the gas is not anymore gas. It becomes liquid and then solid. So you cannot use the gas law for such gas. So this is not always true, you should remember. This is true in our temperatures. Good. Next law is a molar volume law. Saying that the volume of any gas is equal to the number of moles multiplied by the volume of 1 mole. This is kind of boring law, except the fact that the volume of 1 mole is constant for any gas. So which is also showing that the volume of any gas depends only on the number of moles of the gas inside. So this is number of moles, and this one is the molar volume. Also defined as a volume of 1 mole of gas. Well, if I say it's constant, what does it mean it's constant? This is a bit more complicated story, because Vm is constant at given T and P. It means at different values of temperature and different values of pressure will be different. And now again, what is the value at different temperatures and different pressures is given in your book in table 4.3. And let's just copy this table to the blackboard. We have different condition for T and different condition for P. And we have different conditions for Vm. So let's just go. First one is 0 Kelvin. And the pressure 0, I believe, okay, just 0, whatever it is. And the molar volume is 0. So they just assume that every gas would go to 0. I already explained you that this is not true, because before gas going to 0, it will liquefy and solidify. But that's the assumption. That's used just in the calculations. Let's go further. At 0 Celsius and the pressure of 1 atmosphere, you have the number 22.4141 of liter. So first we see when the temperature changed by 25 degrees, the volume changed by 2 liters. Well, quite a lot. Now be careful. These numbers are different and different temperatures and different pressures. Be always sure which one you are using for solving exercises. Otherwise you get wrong results. Now some of these conditions, some of these temperature and pressures have special names. 1 atmosphere and 0 are usually called as STP, which is for standard temperature and pressure conditions. This one is called SATP, and it's called standard ambient temperature and pressure conditions. Now, it is almost sure that one of the exams questions at the final will be calculate something at STP or calculate something at SATP. They don't tell you what is the temperature and pressure, you should know. So these are things to remember, very hard, at least until the end of this class. Good. Next thing, these 3 laws that I gave you, they combine together to something what is called ideal gas law, which is saying that P and V equal to N T constant at any temperature, any volume, and any pressure. This constant is usually written as R. And the value of the constant R is given in the table 4.2. And I just give you one of them. You can have in other units too. R equal H.20574 times 10 to minus 2 liter times atmosphere divided by Kelvin times mole. Now be very careful. Instead of atmosphere can be bar here. Instead of atmosphere can be Pascal here. When you will be using it for solving exercises, always check what are the units. If you use the wrong unit, you get wrong result. And this very often happens that half of the results in the final are gone because you use wrong units. Good. That's everything for today. We'll continue at the next class.